Okay, so this is complex numbers for A2Further. First of all, just a little bit of a reminder about some of the stuff that we've done then from last year. We know about our complex numbers, for example, 3 plus 4i. What we learned towards the end of last year's topic was another way of writing your complex number was in mod arc form, where you can have z equals r upon cos theta plus I sine theta, where r is the modulus, so that's the length of the vector line, and theta then is the argument, so that's the angle that it makes it with a positive x-axis. Whenever you multiply two complex numbers in this form, you multiply their moduli and you add their arguments. Similarly, if you're dividing two complex numbers that are in this form, you divide their moduli and you subtract their arguments. We then went through this example here. This is actually from last year's notes as well, so let's take a quick run through it and see how we get on. It's asked then for kind of Z1, Z2. So Z1, Z2 is going to be the 9 times 5, because you multiply the moduli, and then we're going to add the argument, so it's going to be cos 7 pi over 12 plus 2 pi over 3 plus I sine 7 pi over 12 plus 2 pi over 3. And extend the bracket from there. If we start to tidy this up, 9 times 5 of course is 45. And that's going to cancel down. If you add those together, you change that's going to get 8 pi over 12. Add them together, you get 15 pi over 12. And that changes into 5 pi over 4 plus I sine 5 pi over 4. The argument, of course, needs to be between minus pi and pi, and that's over pi. So we need to rewrite that as minus 3 pi over 4 plus I sine minus 3 pi over 4. And then we can actually do a wee move here using some trigonometry. So that's the same as 45 cos 3 pi over 4. Say for example you have cos of minus 30. If we change back to degrees just for a second, that's always going to be the same as cos of 30. If you think about the graph of cos, any angle to the right is going to be the same as any angle to the left, because it's symmetrical about the y-axis. And the rule then for the sine one is that sine of minus 30 is the same as minus sine 30, for example. So we can take the minus from that out the front. We get sine 3 pi over 4. This is just handy whenever we're trying to change it into this form here, which is what we've been asked for. So that gives us 45 upon cos 3 pi over 4. You put in your calculator, you'll get minus 1 over root 2 and minus 1 over root 2i, and then tidying that up, finally you'll get minus 45 over root 2 minus 45 all over root 2i. On then to our next page, and this introduces then another way of writing our complex numbers. So the new one that we've just learned is that you can write it in the form r cos theta plus I sine theta. From chapter 5, which you won't have done yet obviously, this expands out, and if you expand out e to the I theta, this isn't for now because we'll do it whenever we do a Maclaurin series. It's 1 plus I theta plus I theta. This is the way e to the x expands out, all over 2 factorial plus I theta cubed over 3 factorial plus I theta to the r over r factorial. Also learn that you can expand out the cos theta and the I sine theta. And you can, our third way then of writing our complex number is r e to the I theta. So you also learn that e to the I theta is cos theta plus I sine theta. This is a useful result you should remember. Now the modulus argument form of a complex number z equals r cos theta plus I sine theta. So you can write the complex number in a third form, namely, and there should be a wee r in there, it's a wee typo, So z equals r e to the I theta, where r is the modulus of z and theta is the argument z. This is called the exponential form of a complex number. Okay. Quickly then on to De Moivre's theorem, and we'll just give it a quick mention, and we'll then try and move on from there. So this quickly runs through, and I'm not going to do the whole thing, but this runs through that, of course, if you multiply two complex numbers, that you multiply your arguments and you add you multiply their moduli and you add their arguments. So if you have something squared, then it's going to be the r squared, and then it's going to be 2 times the theta, so that's 2 theta. Similarly then for r cubed, it would be r cubed. Sorry, if z cubed, say you had the cubic complex number, it'll be r times r times r, obviously, that's a rule, and then it's going to be 3 theta, and I can work its way up. And De Moivre's theorem simply states that z to the n, then is a wee bit fuzzy, but hopefully you can read it okay. Z to the n is r cos theta plus I sine theta to the n. So we put our r to the n cos n theta plus I sine n theta. It's pretty much an extension of the rules of multiplying two complex numbers. And I hope that makes sense okay.